Okay, so we're doing a couple different and unrelated things today. Actually, I mean, they are related in some fashion, so yeah, you'll see. Okay, so let's go back to limits for just a very brief period, okay? We always try substitution first, okay? And then we often run into some indeterminate forms when using substitution. Now, there are two types of indeterminate forms. When I'm finding a limit as x goes to a or x goes to infinity of a quotient like this, we sometimes get stuck in a situation like that or that, for example, right? We're stuck once we run into something like that. Okay, so back in chapter 2, we learned some tricks to handle those situations to finish finding the limits. For example, when we got stuck on something like that, it was often helpful to factor and cancel, multiply by the conjugate and so on. Remember all those tricks? Okay, well, and then there were other tricks and things to look for limits that went to infinity. Do you remember looking at the coefficients and the degrees and all that for those situations? Do you remember those? Okay, well, today we're going to learn a new rule to help us find the limit when we run into any of the following indeterminate forms. Okay? So again, it doesn't matter if you're taking a limit as x goes to a value from either side or to infinity or negative infinity. Okay, so as x goes to any of those and you're taking the limit of a quotient and you run into any of these, okay, any kind of combination of infinities over negative infinities, right? Actually, I forgot just plain old infinity as well. Okay? So if you run into any of these indeterminate forms where you're kind of stuck, right? Then you can use this new trick, so to speak, called L'Hopital's rule. Okay? Again, don't pronounce it as L'Hospital. It's L'Hopital is how you say it. Okay? Okay? And so it's real simple, you guys. You're going to like this because when you run into any of those, what you can do is you can take the derivative of the top and the derivative of the bottom and then find the limit again. If you run into, and so one of two things are going to happen. You then try and find the limit again. If you get a number, you're done, right? And that's the limit. Or if you get the limit, you're done. If you're still not able to find the limit and you run into one of these forms again, guess what? You can use the L'Hopital's rule again by again taking the derivative of the numerator and taking the derivative of the denominator and then trying to find the limit again. Okay, you can keep using this as many times as you need to until you can eventually find the limit. Does that make sense? Okay, so here's an example. I asked you to find that limit. Okay, so what happens when I try substitution? What do I get? I get 0 over 0, which means I'm stuck, right? But I'm stuck in a situation where I can use the L'Hopital's rule, aren't I? Yes? So what I did is took the derivative of that. What's the derivative of what's the derivative of ln of x? 1 over x. And then what's the derivative of that? 1. And so this whole thing turns into that. Now, at that point, I'm going to try and find the limit again. So what's the limit of 1 over x as x goes to 1? Well, by substitution, it gives you what? 1. And you're done. See how I can simply use the L'Hopital's rule there to get unstuck? Okay? Okay? All right. And so let's look at example 2. Again, if I try and find this limit, basically, what does e to the x go to as x goes to infinity? Well, there's a graph of e to the x. So as x goes to infinity, what is the numerator going to? Infinity. What about x squared? As x goes to infinity, what's x squared going to? Infinity. So we're stuck, aren't we? Right? We have an indeterminate form. However, we have an indeterminate form where we can use the L'Hopital's rule, right? Yes? So everybody then, I take the derivative of the numerator. What's the derivative of e to the x? E to the x. What's the derivative of x squared? 2x. Okay, now if I take the limit again, after doing that, again, don't I get infinity over infinity again? So I'm still stuck. So what do? Do it again. What's the derivative e to the x? E to the x. What's the derivative of 2x? 2. Okay? So now, if I take the limit of the top, what's the derivative? I'm sorry, not the derivative. If I take the limit of e to the x as x goes to infinity, yes? No, I'm not taking the derivative of the whole fraction. This is not the quotient rule. I'm not taking the derivative of the whole fraction. I'm taking the limit of the numerator, and I'm taking the limit of the denominator. That's what L'Hopital's rule says to do. This has nothing to do with the quotient rule or taking the derivative of the whole fraction. That's not what I'm doing. Good question, because students often, mix this up, and they do use a quotient rule instead of what I'm showing you, which is just take the derivative of the top, take the derivative of the bottom. Now again, I'm not finding the derivative of the whole fraction. That's not what I'm doing. I'm using L'Hopital's rule, which says you take the limit of the you take the derivative of the numerator over the derivative of the denominator, and then take the limit again. Is that clear? Okay. All right, so what's the limit of that as x goes to infinity? Infinity. What's the limit of that? 2. Well, if the top's going to infinity and the bottom's going to 2, what's the whole fraction doing? It's going to what? Infinity. Got that, guys? Okay. Okay, let's look at example 3. Okay, so again, by the way, on something like this, you can take the limit of that as x goes to negative infinity and the limit of that. And what's happening is the first one's getting bigger and the second one's getting smaller. And so are you able to find out what's happening to a product for sure if one's getting bigger and one's getting smaller? No. So we're stuck. Okay, but now L'Hopital's rule does not work on a product, does it? It only works on a what? Quotient, right? So, but I can get creative and turn that into a quotient. So is it okay if I use algebra 1 to rewrite that as that? You see how I turned it into a quotient? See what I did there? Okay, Anthony, can you keep your head up for me? Up, up, up. Okay. All right, so by the way, what happens now when I take the limit of that thing? What do I get? As x goes to negative infinity, that's going to infinity, and that's going to what? What is, well, you should know what e to the negative x looks like. That looks like this, doesn't it? Isn't that what the graph of e to the negative x looks like? So as x goes to negative infinity, what are the y values going to, guys? Positive infinity. So everybody agree you get stuck again with positive infinity over positive infinity? Everybody agree? So can I use L'Hopital's rule now? Okay, so quickly, what's the derivative of the top? What's the derivative of x squared? 2x. What's the derivative of the bottom? Well, e to negative x times the derivative of negative x, which is a negative 1, and so I get that. And by the way, if you try substitution again, you're still stuck. But at least you're still stuck in some form where you can use L'Hopital's rule again, right? So here we go. What's the derivative of 2x? Quick. 2. What's the derivative of this? Well, if you do the derivative, it's e to the negative x. Okay, now when you take the limit of the top, you get 2. When you take the limit of the bottom, you get infinity. So if the top's going to 2 and the bottom's getting bigger, what's the whole fraction doing? It's getting smaller, isn't it? And going to what? 0. So again, by turning the product into a quotient, realizing it fits L'Hopital's rule form, I used L'Hopital's rule there a couple times until I was eventually able to find the limit. Is that clear? Yes? Okay. But again, I want you guys to understand, the only time you can use L'Hopital's rule is when? Here. I can't emphasize that enough. Got it? It's not just any time you get stuck. It's only when you get this kind of stuck. Is that clear? Yes? Or no? Yes. Okay. All right, so now that you know L'Hopital's rule, you can use it in one little piece of what I'm about to show you. So here's what we're going to do now, guys. This is where you guys become almost as powerful as your graphing calculators. we're going to go back to stuff we did at the beginning of the year in the summer packet, which was Algebra 2 and pre-calc stuff, right? And we're going to use almost everything I've taught you to this point with calculus. And we're going to combine everything then that we've done this year. And we're now going to be able to sketch graphs of functions that you probably couldn't have done before without a graphing calculator. Are you ready? Christine, ready? Okay, so here we go. Okay, so one valuable thing to find when you're trying to graph a function is to find the what? Intercepts. And again, that's just Algebra 1 and Algebra 2 stuff is all that is, right? Okay, symmetry is also helpful, right? Because if you know a graph has symmetry and you know what half of it looks like, you can draw the other half, right? Based on symmetry? Yes? And by the way, how do you test for symmetry? Well, you would just replace x with negative x in the function and play around with it. If you get the same original function back, then it has what? What type of symmetry? Y-axis. What happens if you replace x with negative x in the function and play around with it, and you're able to determine you get the complete opposite of the starting function? Then it has what? Origin symmetry, right? Got it? What else might be helpful? Asymptotes, right? And you should know how to find both vertical and horizontal asymptotes. Okay? So to find vertical asymptotes, okay, if you remember we talked about vertical asymptotes. When the one-sided limits approach infinity and negative infinity, isn't that when I get vertical asymptotes? By the way, there's an easier way to find vertical asymptotes. What's the easier way to find vertical asymptotes? Just find the what? For rational functions, we can just find what? The what? Non-removable discontinuities. Isn't that when you're going to have a vertical asymptote? Right? So instead of actually finding these limits, just find the non-removable discontinuities, and those will be your vertical asymptotes. Following me? Okay. And then how do you find horizontal asymptotes? So that was all on vertical asymptotes. How do you find horizontal asymptotes, guys? Well, you do have to find these limits. Okay? You must find these limits to find all horizontal asymptotes. So take the limit as x goes infinity or negative infinity, and if you get a number, L, then you have a horizontal asymptote at y equals L. Got it, guys? Okay, then we move into the more recent stuff, which are your what? Your hills and valleys, and where f is increasing, decreasing, right? And again, there are two ways to do that. You can use the first derivative test with a table, right? Yes? Or if you want to avoid the table, you can try the second derivative test. It's up to you. Okay? But you got to do one or the other. That's the only way to find your hills and valleys, right? I'll tell you right now, chances are I'm gonna make you, or I'm not gonna make you, but chances are you're gonna want to use that. Okay? Because not only does that tell you your hills and valleys, it also tells you where f is increasing and decreasing, right? So chances are you're going to use that one and not so much here. Okay? With me? Okay? And then number 5, knowing the concavity would help as well. And how do you find that? How do you find where f is concave up or down? Well, you start by finding where what? Where what? F double prime is 0 undefined. And then you get your test intervals. On an interval, if f double prime is positive, f is concave up. If f double prime is negative, f is concave down. And by the way, going back to number 4, where do you start there? You start with finding x values where f prime is 0 or undefined. And then break up the number line into your test intervals. Are you following me? Yes? Okay, so here's how it's going to go then. Okay, so this is what we're going to do here. Number 1, we're going to create a table by breaking up the number line to test intervals by using all x values from these 2 steps. In the past, we never did these together. We always did one or the other. We were either finding hills or valleys or we're finding inflection points, but we never did them together. We are going to do them together today. Is that clear? So we're going to do 4 and 5 together, which means anywhere where f prime or f double prime is 0 undefined is what you're going to use to break up your number line into test intervals. Okay? All right, then number 2, you can sketch the graph by plotting the intercepts, plot all endpoints of the intervals, And then finally, fill in the rest of the table, or I'm sorry, fill in the rest of the sketch based on the information you get in your table. Okay, so that's what we're going to be doing in our last couple examples. Are you ready? Guys, I know it's hot in here. I sent them an email yesterday. They said they were on it, so I don't know what's going on. Okay. I know it's hard to concentrate when it's this hard. Or when it's this hot. It's hard for me too, but do your best. Maybe give yourself a little slap in the face or something. I don't know. Whatever it takes, okay? Got it? Here we go. Sketch a graph of this function, okay? So here we go. First thing I'm going to do is find the what? Intercepts. Ready, guys? Okay. So this is where you need to start writing stuff down, right? All right, so the intercepts are 0, something, and something 0, correct? Okay, so if I put a 0 in there and a 0 in there, what do I get for the y value? If I stick a 0 in for x, guys, what do I get for the y value? Quick, 0. Okay, what if I stick in a 0 for y now? Well, that would give me this, right? And by the way, you can pull out a what? A 4 and a what? X squared, and it leaves you with what? X minus what? 3. And so when will this be 0? When x is 0 or when x is what? 3. Okay, so by the way, that's just a repeat. So we only have 2 intercepts, right? 0, 0, and what? 3, 0. So go down your graph and plot them. 0, 0, and 3, 0. But do you agree? So you guys, aren't those the only places where your graph can cross the x or the y-axis, aren't they? Yeah. Those are the only intercepts we found, so those are the only places where your graph can cross the x or y-axis. Is that clear? Yes? Okay. Let's test for symmetry. So I take the limit as x goes to infinity. No, I'm sorry. I'm doing asymptotes. To find symmetry, you replace x with negative x. Sorry about that, guys. Play around with it and see what it turns into. Ready? When I cube a negative, doesn't that stay negative there? So don't you get negative 4x cubed? And when I square negative, it turns positive, but so I still end up with a minus 12x squared. Okay? All right, now what I want you to do is I want you to compare that with the original f of x. Are those the same? No. If I pull out a negative, will it give you the exact opposite of what you started with? No. So guess what? No symmetry. Okay. Now, you can find the asymptotes by taking the limit as x goes to infinity or negative infinity. But this is how you find the what? This is how you find the what? Oh, I'm sorry. I'm writing the wrong function. Sorry, guys. This is how you find the what? Horizontal asymptotes, right? Yes? And by the way, the only way you're going to get a horizontal asymptote if this turns out to be a number. Is there any way these are going to turn out to be a number? No. Right? So you're not going to have any horizontal asymptotes. By the way, it's a polynomial anyway. You know there's no horizontal asymptotes, are there? Yes, question.
Does this have to do with the fact that polynomials are always continuous?
Right. Right. Exactly. Right. Again, so polynomials, there's no way you're going to have asymptotes, are you? No. And so you're not going to have any asymptotes. What about, and again, but you got to check for vertical and horizontal asymptotes. So again, this is checking for horizontal asymptotes. The only way you can have a horizontal asymptote if these turn out to be a number. So these are not a number. Because these are not a number, there's no way you're going to have a horizontal asymptote. And the only way you're going to have a vertical asymptote would be if you'd have a non-removable discontinuity. Well, polynomials don't have any discontinuity. So again, there'd be no vertical asymptotes either, right? Got it? So no vertical asymptotes and no what? Horizontal asymptotes. No vertical asymptotes, no horizontal asymptotes. Understand? But you got to check for them on other functions, right? Okay? All right, now we want to make our table. So we're going to find all values where what? F prime is 0 undefined or F double prime is 0 or undefined. Are you ready? Ready? Okay. So what's F prime? Quick, guys. What's F prime? 12x squared minus 24x. And by the way, that factors into what? 12x times x minus 2. Okay, so where is that 0 or undefined? At 0 and what? 2. Okay, now what's F double prime? Quick. 24x minus 24, which is 24 times x minus 1. So where is that 0 or undefined? At 1. Okay, so we're going to use all these values now to break up my number line into test intervals. Are you ready? Are you ready? Here it goes. Okay, so I'm going to go from negative infinity to what? What's the first one I run into? Quick, quick, quick. 0. Then the pick up there and go to what? 1. Pick up there and go to what? 2. Pick up there and go to infinity. Okay, so pick anything in here you want. Okay, now I'm going to stick these into F prime and F double prime because I want to see everything. I want to know whether F is increasing or decreasing on these intervals, and at the same time, I'd like to know whether F is concave up or down on those intervals. So again, in the past, I never asked you to do these at the same time, but that's what we're doing today because we want to use this information to graph it, right? So don't I need to know both to be able to graph it? Yes? You see what I'm doing and why I'm doing it? Don't just memorize. You see why I'm doing what I'm doing? Okay, so here we go. Quick. Help me, guys. If I stick negative 1 into F prime right here, quickly, is that positive or negative? Quick, quick, quick. Positive. What if I stick it into F double prime? Positive or negative? Negative. Okay, let me stop for a second there. If F prime is positive and F double prime is negative on the interval, what can you say about F? F is what? Increasing and what? Concave what? Down. You with me? Okay, just keep doing this. Okay, so what do I get when I stick a 0.5 in? Quick, help me. Negative. What if I stick a 0.5 there? Negative. So what can you say about F on that interval, guys? F is what? Decreasing and what? And concave down. Okay, stick a 1.5 into F prime and then F double prime. Quick, what do I get here? F prime is what? Negative. F double prime is what? Positive. So what can you say about F on that interval? F is what? Decreasing and what? Concave up. And then finally, if I stick a 3 into there, see, F prime is what? Positive, and F double prime is what? Positive. So therefore, F is what? Increasing and what? Concave up. Yes? Yes or no? Good, good, good? Yes? All right, now there's one extra thing here that you absolutely must do, because without this, you're not going to be able to connect the dots. You're not going to have enough dots to connect. So how do I get some more dots to connect? Well, wouldn't it make sense to figure out what the y value is on F at these breaking points? Wouldn't that make sense if I'm trying to draw a graph? Wouldn't that be a next wise move? Yes? Okay, so quickly, if I stick 0 into F, what do I get for the y value? Quick, quick, quick. 0. Okay. If I stick 1 into F, quick, what do I get? Negative 8. And if I stick a 2 into F, quickly, what do I get? Let's see. see, 2 cubed is 8. 32 minus 48, negative 16. Yes or no? Okay. All right, so now what I want you to do is I want you to plot these points to give you some more dots to connect. Is that clear? Okay. So 0, 0 is already there. 1, negative 8 would be, let me label this. Okay, so we've got 2, negative 16, which would be right about here, right? Everybody agree? Okay, and then 1, negative 8. I didn't do that yet. 1, negative 8 would be about here. Got it, guys? Okay. Following me or no? Okay, so here we go. So, one at a time. I'm going to take the intervals now and I'm going to fill it in on the graph. Ready? Here it goes. What does that tell me there? Between negative infinity and 0, what can you say about f? It's what? Increasing and what? Concave down. So use that along with a little common sense, and that'll tell you that it's got to look something like that. Isn't that increasing from left to right and concave down? Yes? Okay, now, between 0 and 1, what's happening? F is what? Decreasing and what? Concave down. And I have to connect those 2 points at the same time, don't I? So isn't that decreasing and concave down? Yes? And how about between 1 and 2? F is decreasing and concave what? Up. So it's going to look more like that, isn't it? Isn't that decreasing and concave up as I connect those 2 points between 1 and 2? Are you following me? And then finally, from 2 all the way to infinity, F should be doing what? Increasing and being what? Concave up. And at the same time, it's got to pass through that point along the way, doesn't it? Yes? It's just going to look something like this. So you can always check it by graphing on your calculator. So I'm just going to graph the original function, right? Okay, so that's what I say it looks like. Let's see what my calculator says it looks like. Ready? What do you think? Think we did pretty good on our own without the calculator? Yep. Good? Cool, huh? Okay. All right, we'll do one more and that'll be it. All right, now I want to do one where it's a rational function just so you can handle that, okay? So I'm giving you one example of a polynomial. I'm giving you another example of a rational, so just to give you a good variety of examples, right? Okay, so here we go. Ready, guys? Okay, so let me call on you guys and you can help me out here. All right, Henry, how do I find intercepts? Okay. So if I put a 0 in for x here, what do I get for the y value? 0. Okay, if I stick 0 in for y, I get this, don't I? And go ahead, Henry. When is that fraction going to be 0? Yeah, when the top is 0, which is at x equals 0. And so that's it. Those are the same. And so I only have one intercept on the entire graph. Everybody agree with that? So when you go down to your graph, this, guys, is the only point where the graph could cross the y-axis or the x-axis. Nowhere else. Do you agree with that? Because that's the only intercept I found. So that's the only place the graph can cross the x or y-axis. Agreed? Okay. All right, what else? Symmetry. Okay, well, to test for symmetry, you replace what? What do I do, Takul? Replace what? X with what? Negative x. And then play around with it and see what happens, right? So I get that, and again, compare that to what you started with. Is that the same function, yes or no? No. If I pull a negative out on the bottom and cancel it with the negative on top, yes, thank you, and cancel the negative, I end up with this. Is that the same as what I started with? No. Is it the complete opposite of what I started with? No. So this has what? No symmetry. You guys, do you realize, I mean, suppose it had some kind of symmetry. Well then, I'd only need to fill in half of my table, right? And then just kind of reflect the graph to fill out the other half. Do you see why symmetry might come in handy? Like if you had a big long table and you're able to determine it has symmetry, you can fill out half the table, draw it, and then just flip it or do whatever you got to do to draw the rest of it. You see why symmetry might help, especially in a really long problem like this, right? Got it? Okay. All right. So, Sam, how do you test for asymptotes? Well, let's start with vertical asymptotes. Yeah, you'll have vertical asymptotes where you're right, where the denominator is 0, and not only it's 0, but you can't do any kind of algebraic maneuvers to cancel out that discontinuity, right? And so you're right. You do have a discontinuity at x equals 3. Is there any way to algebraically manipulate this to where I can cancel out that factor x minus 3? No. So that makes it a what? A vertical asymptote, right? Non-removable discontinuities are vertical asymptotes. So go down your graph and at x equals positive 3, draw your vertical asymptote. Everybody agree? Okay, now, to find horizontal asymptotes, by the way, make a note that that's a non-removable discontinuity. That's why that was my vertical asymptote. Okay, for horizontal asymptotes, you take the limit as x goes to infinity and the limit as x goes to negative infinity. And again, you can use your old shortcuts or you can use the L'Hopital's rule. I don't care. It's up to you. I'm going to use my old shortcut. Since I'm going to infinity, and this degree is the same as that degree, then what's the limit? Isn't it leading coefficient over leading coefficient? So the limit here is what? 2. Same thing here, isn't it? Yes? So you have a horizontal asymptote at what? At what? Y equals 2. Everybody agree you have a horizontal asymptote at y equals 2? Okay, this is all review. I'm just putting it all together into one problem. Yes? Okay, again, when we learned about horizontal asymptotes in a previous chapter, we said that the only time you have horizontal asymptotes is when you take the limit as x goes infinity or negative infinity and you get a number. And so I took the limit of that, and there was a shortcut that we learned in the past that when you're taking the limit as x goes to infinity or negative infinity, you look at the degrees. If they're the same, then the limit is leading coefficient over leading coefficient. What if the bottom had a higher degree than the top? Then the limit would be what? 0, and you would have had a horizontal asymptote at y equals 0 instead. Does that make sense? Agreed? Okay? All right, so I want you to go down to your graph now and draw a horizontal asymptote at y equals 2. But you see what I'm doing here? Okay? All right, now what? Now I got to take the derivative, right? And find first and second derivative and find where f prime and f double prime are 0 or undefined. And this is going to be the tricky part. So here it goes. All right, ready, guys? Here we go. So clearly I'm using the quotient rule. Okay, you guys can check my work on that. I mean,
-3.
trying to rush too much. Thank you. Okay, we good on that, guys? Yeah? Okay. And now I'm going to use that to find f double prime, right? Now, you guys, you could use the quotient rule. However, and by the way, if there was a variable there, you would have no choice but to use the quotient rule, right? However, because that's a constant, because that numerator is a constant, would it be okay to just use algebra 1 to rewrite it like that? And then you realize that you don't need the product rule because there's no variable there. So I don't need the product rule, I just need the what? Chain rule. Does that make sense? So I can just use the chain rule instead of the product or quotient rule here? You agreed? Again, does everybody understand if that was a 6x, I wouldn't be able to make it this simple, would I? No. Okay, so don't you just bring down the exponent, right? Subtract 1 from the exponent, put the inside back in, and then don't forget to multiply by the derivative of the inside, which is that. Okay, and so there's f double prime. Everybody agree that's f double prime? Sorry, this is f prime. This is f double prime. Sorry about that. Okay, guys? All right, so you guys, I want you to look at those derivatives and tell me at what x value is the first derivative undefined or 0? 3. What about the second derivative? 3. So you only have one number to use to break up your number line into test intervals. That's kind of nice, isn't it? Okay, with me, Anthony, okay? Okay. So let me go back to my paper and let me write these down. Okay, so here we go. So I'm only going to use x equals 3. Any questions? I mean, I know I'm going fast, but most of this is review, so I'm assuming you don't have a lot of questions. Please stop me if you do. Are we good? I know I'm going fast, but am I good or no? Okay, here we go. Okay, so pick a test value here. Pick a test value here. Stick them into f prime and f double prime. So if I stick a 0 there, clearly this is negative, right? Stick a 0 there, I get negative, don't I? And therefore f is what? Decreasing and what? Concave down. Agreed, guys? Okay, over here, if I stick a 4 into f prime, I get a what? I'm sorry, a negative again. If I stick a 4 into f double prime, I get a positive. So therefore, on that interval, you can say that f is decreasing and what? Concave down. No, concave what? Up. Decreasing and concave up. Okay. And by the way, I'd like at least more dots if I can find them. So where am I going to get some other points from? By plugging what? The endpoints of my intervals into f to get another point on the graph of f. So if I stick a 3 into f, what do I get for the y value? I get undefined. Okay, so there are no other points to use. Ready? Okay, so all the way from negative infinity to 3, the graph has to be what? Decreasing and concave down, and it has to pass through that point. Yes? So using common sense, doesn't it have to go along the asymptotes like that as it passes through that point? Doesn't it? Isn't that the only possible way it can look? Isn't it? Okay, now, what about from 3 to infinity? F has to be what? Decreasing and what? Concave up. So what would be the only way that would make sense? You're either going to draw it up here or down here. Above. Again, I guess you could have gotten 1 point in here if you wanted, but whatever. It's going to look something like that, isn't it? Why couldn't it possibly be down here? Well, many reasons. Well, you could never draw something down here that would be decreasing concave up. Also, if it was here along the asymptote, wouldn't it cross the x-axis again, which we know it can't happen, right? Because we found all the intercepts already. So just by little common sense and calculus and algebra, we were able to figure out what that graph looks like. And again, you could graph it on your calculator. Check me on that. Are we good? Okay.